Like axioms, postulates are also statements that are assumed without proof. However, unlike axioms that are general statements, postulates are specific to geometry. Moreover, postulates assert that something exists, whereas axioms do not. For example, an axiom states a self-evident truth, such as, if equals are added to equals, the wholes are equal. Postulates, such as the first one, a straight line may be drawn from any one point to any other point, asserts the existence of a straight line. Let's explore more about Euclid's postulates. Let's say we have multiple points. Can we connect any two points? Yes, we can draw a straight line between any 2 points. This is what Euclid's first postulate states. It states that a straight line may be drawn from any one point to any other point. Now, let's take this line segment PQ and extend it on both sides. As you can see, we can go on extending this line indefinitely. So, we come to Euclid's second postulate, which states that a terminated line can be produced indefinitely. What Euclid calls a terminated line is a line segment. So this postulate states that a line segment can be extended continuously and infinitely in a straight line. In a way, this could mean that space is infinite. Next, let's draw a circle with a certain radius. Now, with a point on the circle as center and an increase in the radius, we draw another circle. With a point in the exterior of these circles as center, let's draw a circle. Now, with a point in the interior of the circle as center and by decreasing the radius, we draw a circle. Therefore, it is possible to draw a circle with any center and any radius. That's what Euclid stated in his third postulate. A circle can be drawn with any center and any radius. As the earlier postulates assert the existence of straight lines, this postulate asserts the existence of a circle. It allows for the existence of circles of any size and center. Euclid's next postulate asserts the existence of right angles. Observe that all right angles are equal because each angle has a measure of 90 degrees. That's what the fourth postulate states. All right angles are equal. Why did Euclid mention only about right angles? Why not 30-degree angles or 120-degree angles or other measures of angles? Perhaps this could be because Euclid uses a right angle as a unit to measure other angles with. Euclid defines right angles and perpendicular lines in his treatise, Elements. He also uses right angles to define obtuse angles as those greater than a right angle, and acute angles as those smaller than a right angle. Moreover, Euclid uses the right angle as a unit of measure for his fifth postulate. Euclid's fifth postulate is a little difficult to understand in terms of its wording. So, first let's take an example before we go on to the postulate. Two lines, L and M, are intersected by another line, N, at points X and Y. Two interior angles, say one measuring 80 degrees and the other measuring 70 degrees, are formed on the same side of line N. Will lines L and M intersect? If yes, will they intersect on the same side where sum of the measures of the interior angles is less than 180 degrees? If the lines L and M are extended, then they meet at point Z. Observe that the point of intersection is on the same side, where the sum of the interior angles formed at the points X and Y is less than 180 degrees, or less than the sum of two right angles. However, if the sum of the interior angles X and Y is 180 degrees, then the lines L and M will never meet, that is, L and M will be parallel. This observation is presented by Euclid in the form of his fifth postulate. It states that if a straight line falling on two straight lines makes the interior angles on the same side of it taken together less than two right angles, then the two straight lines, if produced indefinitely, meet on that side on which the sum of the angles is less than two right angles. Euclid's fifth postulate is more convoluted as compared to the other four postulates. Therefore, it has been researched by many mathematicians. As a result, many adaptations of this postulate exist. Let's study some of them. One of the alternative versions of Euclid's fifth postulate was given by a Scottish mathematician, John Playfair, in the form of an axiom. According to the axiom, given a line and a point not on the line, it is possible to draw exactly one line through the given point parallel to the line. In other words, for every line x and for every point A not lying on x, there exists a unique line y passing through A and parallel to x. Let's draw several lines passing through the point A. Observe that amongst all the lines, only one line y is parallel to x. The other lines passing through point A, except line y, are not parallel to line x. Hence, Playfair's axiom can also be stated as two distinct intersecting lines cannot be parallel to the same line. While Playfair's axiom mentions parallel lines, Euclid's fifth postulate does not explicitly specify parallel lines. Yet, in a way, Euclid's fifth postulate connotes the existence of parallel lines. Let's see how. Consider line n meets two straight lines, L and M, at two distinct points. The sum of the interior angles 1 and 2 on one side of line n is equal to 180 degrees, or 2 right angles. Now, let's apply Euclid's fifth postulate to this situation. If the sum of the two interior angles 1 and 2 on the same side of line n is less than 180 degrees, then the two straight lines L and M meet on the same side as the angles 1 and 2. However, in this case, the sum of the interior angles 1 and 2 is 180 degrees. Thus, we can say that the two lines L and M do not meet on the side of angles 1 and 2. Now, let's check the sum of the angles on the other side of line N. The sum of the interior angles on the other side of line N is also equal to 180 degrees, or 2 right angles. Therefore, lines L and M cannot intersect each other on the other side of line N2. As lines L and M do not intersect each other on both sides of line N, lines L and M are parallel to each other. Thus, parallel lines are indirectly implied from Euclid's fifth postulate. Did you know that all the attempts to prove Euclid's fifth postulate as a theorem have failed? However, this continuous effort gave rise to the creation of new geometries called non-Euclidean geometry. Our universe is believed to be based on non-Euclidean geometry or spherical geometry. According to spherical geometry, lines are not straight, but they are part of the great circles that are obtained by the intersection of a sphere and plane through the center of the sphere. For instance, the lines PO and QO are perpendicular to the same line PQ. However, lines PO and OQ meet each other because the surface is spherical, and they form a triangle in which the sum of the angles is greater than 180 degrees. Thus, Euclidean geometry does not hold true for this type of situation. Therefore, Euclidean geometry is valid only for figures in a plane, but fails for curved surfaces.